No. In fact, I will talk about some colleagues in the second presentation. I will talk of some colleagues who studied with me in the same institute, and they are recognized researchers. I can share with them. I can say to them, "Oh, maybe you could give a talk with this group if you want."
Yeah. Thank you very much for very nice of you.
Sorry, Will.
It's okay.
Winter practice and I got a cold. So
of
many
course, later
students.
we hope we can have collaboration after this. We can
Of course.
think.
Of course. Yeah. I hope to.
We already have our dean here, Pak Nasrul. Hi, Pak. Pak Nasrul.
Hello, Nasrul. Good morning.
Pak, belum di ini masih di
audio.
Good morning, very good morning in Indonesian time.
Good morning.
How are you, Dr. Alfredo Jaramillo?
Well, thank you.
Am I correct? Jaramillo or Jaramillo?
It's a Spanish name, so it's difficult. It is Jaramillo. Jaramillo. This double L is confusing. Jaramillo.
Jaramillo. Okay.
And you're Nashville, right?
Yes, Nasrul Hakim. Yeah, Nasrul Hakim is actually Arabic name.
Nice to meet you.
Nice to meet you. Thank you very much. So, what time is it right now in the Brazil?
But we are waiting for Gustina as master ceremony, as well as the moderator of this event. Borongan.
9:45 in Brazil, PM. Here in Brazil, it is yesterday for you. Here in Brazil, it's May 25 yet.
Oh, May 25.
In Indonesia is
26 of May already. 7:45 AM morning, Thursday. So
it's so strange.
Okay.
What courses do you offer there in your university? I know that you have pure mathematics, right? But
yes, of course.
Do you have applied sciences?
Yes, we have the basic sciences department also. Actually, in our university, there are 13 faculties and one of the faculty of science technology, and there are 9 study program: basic science, math of course, and then physics, chemistry, and then biology, and then math, physics, biology, chemistry, and then also mining engineering also in the same faculty. Mining engineering, informatics engineering, information system, and then also agribusiness also. Agribusiness, both undergraduate and also master level.
Oh, so you have mining in the
yes, mining engineering.
I didn't know. Oh.
Yes, because we are in the Faculty of Science and Technology, so merge science and technology and engineering also.
Okay, nice. I obtained a degree in applied mathematics, but that is a translation because I did something that is called a career that is called mathematics engineering. So, but it's applied mathematics. You study you do some disciplines on pure mathematics and some disciplines on applied mathematics and statistics and stuff. I'm sorry, I was listening.
Good morning, everyone.
What?
Okay. Gustina.
My voice?
Yeah, okay.
I'm listening some audio. I got
Again.
confused.
Testing again, Yanti.
Ah,
I think
Yanti.
connection problem.
Yanti Gustina. Gustina, yes. Gustina
Whoa.
Connect-
Can you
Alfianti.
hear my voice?
Yes, I am.
There you are, Yanti. Yes,
Is
I'm
my
listening
voice
you.
okay? Is it okay?
Yes.
Okay.
Well, to me it's okay.
Okay. Okay. We
So
will start
we can
this
now.
seminar.
Yeah, we can start now.
Okay, we will start now. Okay. Assalamu'alaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. So, first of, on behalf of the head of Mathematics Department, Faculty of Science and Technology, we delighted to welcome you to the Studium Generale of Mathematics Departments, some mathematical modeling in fluid mechanics with industrial applications. I'm Gustina. I'll be the host of today's seminar. So first, let me welcome our respectable guest. Welcome to Ibu Lili. Ada? Either Bu Lili?
Bu Lili sepertinya nggak ada sih.
Okay. Welcome
Tadi
to Bapak Nasrul Hakim PhD, our dean, and welcome to Dr. Alfredo Jaramillo Palma, our speaker, and welcome to the all lecturer of Faculty of Science and Technology. And last but not least, all the participants of today's seminar. We really appreciate you for taking time off your holiday. Today's is holiday. We hope that we will learn a lot from our speaker. And we have lined up for you to be fruitful and engaging. So first, to begin our seminar, one of our students will recite some verse of the Quran. Please,
Sya'dullah Amin.
Sya'dullah Amin, please, please tune your audio.
Oops.
Paki bisa bikin co-host Sya'dullah Amin.
Langsung.
Ya, langsung aja deh. Langsung aja deh.
Mulai, no?
Ya. Langsung mulai aja. Ya udah, ya. Silakan. I think he is also has a connecting problem. He said before that in his area.
Assalamu'alaikum warahmatullahi. Bismillahirrahmanirrahim. Innal muttaqina fi jannatin wa uyun. Akhidhina ma atahum rabbuhum innahum kanu qabla dhalika muhsinin. كانوا قليلا من الليل ما يهجعون وبالأسحار هم يستغفرون وفي وفي الأرض الموطنين في أنفسهم أفنون وفي السماء رزقكم وما توعدون فورب السماء والأرض إنه لحق مثل ما أنكم تنطقون فورب السماء والأرض إنه لحق مثل ما أنكم تنطقون صدق الله العلي العظيم. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Shadullah. Now let me invite Bapak Nasrul Hakim to deliver his opening speech. Bapak Nasrul, please.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Can you hear me?
Yep.
Yes.
Yeah, Alhamdulillah. Yeah, thank you. Alhamdulillah Rabbil Alamin. Wassalatu wassalamu ala asyrafil anbiya wal mursalin wa ala alihi washabihi ajmain amma ba'du. Invited speaker Dr. Alfredo Jaramillo, researcher of South Carlos School of Engineering, EESC-USP Brazil, and then head of Department of Mathematics, Dr. Sumaina, and also all lecturer, student, and distinguished guests, ladies and gentlemen. Very good morning and welcome you all. I'm very pleased to have this opportunity to say a word at this opening of the Studium Generale, which is held here today, Thursday, 26 May 2022, 8 AM Indonesian time, and in Brazil time, if I'm not mistaken, currently is still Wednesday. Am I right? Wednesday, 25th May 2022, 10 PM.
Yes.
Okay.
Yes.
Yeah, before we get
Like that.
start, yeah, thank you. Before we get start, I would like to introduce myself. My name is Nasul Hakim, Dean of Faculty of Science Technology, Faculty of Science and Technology, or FST, Universitas Islam Negeri Syarif Hidayatullah Jakarta, or UIN Jakarta. That UIN Jakarta is under the Minister of Religious Affairs, Republic of Indonesia. And UIN Jakarta has 13 faculties, including, of course, FST on medical faculty, and then economic and business, and other faculties. And the FST, UIN Jakarta, has 9 study program, as I mentioned earlier, that there are mining engineering, and then informatic engineering, information system, and then agribusiness, both undergraduate and master level, and also basic science, which is physics, biology, chemistry, and of course mathematics, which become host this event today. Okay? Then I would like to express my sincere appreciation to all of you generously help us to make this event come together to become success. Of course, invited speaker Dr. Alfredo Jaramillo, and also head of Department of Mathematics, Dr. Sumaina, and moderator Dr. Gustina Elvianti, and all of you. We couldn't have done it without you, of course. Yeah. And I think without further ado, I declare officially open this event, Studium Generale Online, entitled Some Mathematical Model in Fluid Mechanics with Industrial Application. Today, Thursday, 26 May 2022, 8 AM Indonesian time, by reciting Basmalah. Bismillahirrahmanirrahim. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Nasrul, for welcoming our university and opening our seminar. Now, before we start our seminar, we are going to take a picture first. So for all the participants and our respectable guests, please turn on your camera.
Nice.
And Pak Akib, please help me to take the to capture the screen.
Okay.
Maybe you can start, say, from the first screen.
Let me take the screenshot. First screen, please. Camera on. I will take second screen. Third screen. And last screen. That's it.
Okay, thank you, Bu Sumaina. Now we will start our main agenda. We will divide it for 2 sessions. For the first session, Dr. Alfredo will give a talk entitled Some Mathematical Models in Fluid Mechanics with Industrial Applications. And for the second session, he will share on the opportunities offered by the Institute of Mathematics of Computer Science of the University of Sao Paulo. For each session, there will be about 45 minutes for talk and 15 minutes for question and answer. So before we are going to the first session, let me introduce our honorable speaker. Pak Kip, please help me to share his CV.
Sorry, Auntie, I will do. Just a moment.
Okay, thank you.
Moment, please. Sorry. This is not the one. Okay, go ahead.
Okay, so our today's speaker is Dr. Alfredo Jaramillo Palma. He is a researcher in Sao Carlos School of Engineering, EESC-USP, Sao Carlo, Brazil. He pursued his doctoral degree and master's degree in University of Sao Carlo in Brazil, and he pursued his bachelor degree in Chile. Some of his professional experience since 2019, he is a postdoctoral researcher in Institute of Mathematics and Computer Science, Sao Carlo, Brazil. Sorry, I have problem with the Zoom. Sorry, I have problem with the Zoom.
But in my screen is okay.
I mean, I cannot see the Zoom screen now.
You can probably read on your handphone.
Okay.
Listen you.
Okay. Sorry.
Okay.
Okay, I will continue. And some of his publications, he has many publications. Some of that are entitled "Towards HPG Simulation of Billion Cells Reservoir by Multiscale Mixed Methods," published in Computational Geoscience in 2022. And second is "Detailed Account of Complexity for Implementation of Some Gate-Based Quantum Algorithms," published in Frontier in Physics in 2021. And third is "An Adaptive Time Stepping Algorithm for IMPS with High Order Polynomial Extrapolations," published in Applied Mathematical Modeling in 2022. Oh yeah, Dr. Alfredo right now, and since 2021 until now, is also one of our advisory editorial board journal in Prime, managed by our departments, mathematics departments. And some of his conference, his publication are delivered in some of conference, such as in COBEM 2021 and in Congress Argentino de Mecánica Computacional in 2021. Now we will start the first session. So the time is yours, Dr. Alfredo.
Thank you very much, Gustina. Just confirm me, please, if you're listening, if my audio is working well.
Yes.
Thank you. So I will try to share my screen. Please let me know if that is working. You should see a PDF. Okay, thank you. So the first presentation, for the first presentation, I will talk a bit of the research I have performed during my master's degree and my PhD and a postdoc here at the University of São Paulo. And on the second presentation, I will talk a bit about the opportunities the Institute offers, the Mathematical and Computer Sciences Institute here in the University of São Paulo. So for the first presentation, I'm a specialist in fluid mechanics, and I have worked in the major part of my work, I have performed numerical research. And I will speak a bit of some models I have studied, some mathematical models I have studied. All of them have important industrial applications. Knowing that the focus of this presentation is for undergraduate and graduate students, a very general focus, I will let you know what paths you can follow when you pursue exact sciences or applied sciences career. So you can put on this model, you can ask theoretical questions, numerical questions, and I will try to make emphasis on that. A bit of myself, I did my master degree, as Gustina said. I did my master and my doctoral degree here in the ICMC, the Institute of Mathematical and Computer Sciences in Brazil. Myself, I'm from Chile. There I got my degree in applied mathematics, and I came to Brazil in 2013, pursuing these masters and etc. So I have participated in 4 research groups till now, 2 coming from this period of master or postgraduate studies. Then I did a postdoc here in the institute, in the ICMC, and I'm finishing a second postdoc right now in the San Carlos School of Engineering. And so focusing first in the models I studied during the master and the doctoral research. I worked with lubrication theory. And well, what is it? It is a sub-area of fluid mechanics, where you work with mechanical devices or the modeling of mechanical devices where a fluid is trapped between 2 surfaces, and you put there this fluid in order to diminish friction. Okay, the surfaces are in relative motion between them, and you want to prevent wear. So you want to prevent these surfaces to directly touch each other. So you want to prevent this wear, and you are putting some energy there in the system for this relative movement to continue, right? And you want to prevent, you will have viscous friction, so you will lose some energy. Okay, for this relative movement, you will lose some energy, and you want to diminish this loss, these friction losses, viscous friction losses. Here is one of the main devices when talking of mechanical lubrication or lubrication. It is the journal bearing. It is composed of, let me know please if you are seeing my cursor here. I'm moving it. I'm sorry, I don't have too much experience with Zoom. You're not watching my cursor, right? So at the left side, this axis, this cylinder, it can be handcrafted by steel, for instance, or some metal. So you want this cylinder to rotate, as schematized on the right side, to rotate with some velocity, some angular velocity omega, for instance. So you want it to rotate, but at the same time, you want it to be fixed in space. So you put this this bush around it, made of metal also, some, for instance, steel. You put this to prevent it from moving on the other axes, okay? But of course, you want to prevent this direct contact, as I said. So what you do, what the Egyptians, if I'm not wrong, discovered, that they put some grass, animal fat there, right? And this is lubrication. It can be this fluid that you put there. It can be oil, water, gas. And what happens is that due to the relative movement of the fluid among these two surfaces, a hydrodynamic pressure will appear. This pressure, this hydrodynamic pressure, will support the load that is the load that the journal is suffering. Okay, for instance, its own weight, right? And but you have that's okay, but you have, if you do this surface, the surface of the shaft or the surface of the journal, you can do it, you can manufacture it as being smooth, okay? But during the last decades, many scientific papers have been written around textures, okay, that you can set on both on the bush or on the shaft. And the thing is that you can prove experimentally or numerically, you can prove that these textures, okay, can help on enhancing the friction losses. Okay, so you put the texture and you compare for the results of what happens when you do this surface smooth, and you will see that some textures will help you on reducing the friction losses. Okay, this is too abstract, so let me help a bit with this picture. This is the picture of an actual journal. As you can see, some texture was manufactured there. But the textures, these textures, the depth of these textures is on the scale of microns, so a medium part of a meter, right? So it is, the depth is very small, really small compared to the radius of the journal. The typical radius is around 25 centimeters, the diameter, and this depth is of only around 10 microns. So this is very small, and we have the technology to do that. And as you can see, you have the technology to do basically whatever texture you want. Okay. So from imagining or from thinking some texture, you will have some free design parameters that you can choose, that you can explore, looking for diminishing friction losses. For instance, as in the picture, you can have, for instance, two parameters: the depth of the texture, okay, how profound you will go, and the number of textures you will put. Another parameter would be the width of these textures, right? And you have these three parameters. So, and you want to explore which textures delivers the best results in terms of friction, in terms of wear, okay? And here, for the undergraduate students, here you can go two ways, basically. You can go numerically, or you can go experimentally. Here, for instance, here on this picture, we have 8 possibilities for the same kind of textures. This is called this shape is called chevron. So for these chevron textures, you have, in this case, 8 possibilities. So you can manufacture 8 journals. Okay, these 8 journals, and do the experiment and measure what of these textures delivers the best result. Okay, or you can go numerically, In general, or well, depending on the application, to do this numerically will be cheaper. You will save both money and time, okay? Or you will save on one of these variables. Either it will be cheaper, or it will take less time to perform these simulations, these numerical experiments, if you want. Or you can go experimentally, and of course there is sort of saying some symbiosis, or there can be some symbiosis between doing experiments and doing numerical work. Okay. Down below, you have a numerical result of what is the hydrodynamic pressure for each of these textures. So you can see the hydrodynamic field varies with the texture. And if you integrate this pressure field, you will obtain what is the hydrodynamic support for the journal. Okay, but as you can see, you have many free parameters that you can explore. Let me go back here. So what do you do if you want to go numerically on this exploration? What you do is to abstract this problem. You get some geometrical description of the problem, and you write down mathematical models for the physical phenomena, right? You can go, for instance, writing down the Navier-Stokes equations for the fluid between the surfaces, right? But in the case of lubrication, you have the Reynolds equation that can be proved to be an approximation under the lubrication hypothesis. You can prove that this is in fact, in some sense, an approximation of the Navier-Stokes equations. Navier-Stokes equation, remember, they are 3D. Reynolds equation, the Reynolds equation is 2D. And it is an elliptic equation. If you, let me first say here, h, this function h, you have replaced one of the dimensions by this two-dimensional function h, which describes the gap between the surfaces, okay? So what is the distance between the surfaces is h. Clearly, if the distance between the surfaces is homogeneous, is just a constant, the pressure field is null. You can see from this equation that pressure field is null. So you need some divergent convergent geometry to generate some pressure. That is h. Rho is the fluid density, and so from this equation and from U, which is the speed, the relative speed or velocity of the surfaces, you can obtain the hydrodynamical pressure. So knowing h, knowing rho, this is an elliptic equation for P, and you can go with theoretical questions on it, or numerical questions, how to discretize, how to solve it numerically. But the thing is, for better or for worse, this is not enough, because the fluid, if you apply a negative pressure on a fluid, that is, sort of speaking, if you try to stretch the fluid, okay, you can think of a rope. If you stretch the rope enough, the rope will break. That also happens with fluids. If you stretch enough the fluid, cavitation will take place, and there is a loss of continuity of the fluid. Okay, so these kind of areas will appear. These remarked areas where P is the pressure, the hydrodynamic pressure is approximately the cavitation, some threshold called cavitation pressure, and there the Reynolds equation is not valid anymore. Okay, only when you have full film, when P is higher than this threshold, you have the validity for the Reynolds equation. But there, in these other areas, something else is needed. Something else is needed, and you can prove that something else is needed to have accurate results. And there, the state of the art when modeling cavitation in this context of the Reynolds equation is the Elrod-Adams model. Okay. Elrod and Adams, what they did was to introduce a second unknown. Recall the unknown was the hydrodynamic pressure P. They introduced the unknown theta, which accounts for the fluid fraction. So, and this P and theta accomplish a complementary relation. When the pressure, which can be taken as being null, the pressure is positive only when theta is different only when theta is equal to 1. So, which means full fill. Whatever whenever P is equal to 0, theta is free to be different from 1, so you have cavitation. But this is this time this problem is highly nonlinear because the cavitated area, the cavitated region, is a priori unknown. Okay, so the boundary of the cavitated area, where theta is lower than 1, is an unknown of the problem. This makes part of your mathematical problem. So it is also called a free surface, right? It's a free surface problem. Is a very hard problem to study both theoretically and numerically. And you can see that this time the equation, when theta is lower than 1 in the cavitated area where you are solving for the fluid fraction, the problem is hyperbolic. Okay. On the rest, your problem, you recover the elliptic, analytic problem. So your problem is hyperbolic, okay, depending on which area. And you can go with theoretical. There are theoretical works on it, on existence. Well, in general, the well-posedness of this problem for the mathematicians. There are some papers of the last 10 years. There are also many numerical works. What I did during my master, during my doctoral studies, in part was to try to generalize this model. The thing is that this model only allows for the pressure on the boundary to be null, exactly equal to the cavitation pressure. It doesn't allow for positive pressures on the boundary. And there are some mechanical devices where the pressure is positive, and some important devices like the piston ring cylinder device. And what happens here is that the piston ring, I was thinking of sharing a video. Let me see if I can share a video with you. Well, first let me describe the situation. On the figure on the right, at the left side, there where it says gas, this is a free region that is in contact with the rest of the engine. And at the right side, this gas is in contact with the combustion chamber, there where you are burning gas. Okay, and the ring is there in order to seal the combustion chamber, in order to prevent the gas to go out from this chamber. Okay, and there you have between the ring and the bush, the cylinder, in fact, the cylinder surface, you have some lubricant. Okay. So at the left side, you have 1 atmosphere. The pressure, the mechanical pressure is 1 atmosphere, and on the right side you have a pressure that oscillates and can have peaks as high as 100 atmospheres. So the pressure there is positive. So the Elrod-Adams model will not work there, or will not deliver accurate results. You can solve it with the Elrod-Adams, but then you will dismiss this positive pressure. Let me share a video of this situation. Let me see if I can here. I will try to change the there. I will. There it is. So right, please do like this. You should be seeing a video. So this is what. Please confirm me if you're seeing this video.
Yes, we can see it.
Thank you. Thank you. So this is a dynamic situation. The ring upside, or the surface upside is a ring, and downside we have a textured cylinder that is in relative movement with the ring. In red, I will stop this. In red is the hydrodynamical pressure, and in blue is the fluid fraction. So there, where the blue field is detached from the black surface, there your cavitation is taking place. Okay, you can see pressure. The pressure is 0 there. Otherwise, the pressure is positive, and there the blue line is attached to the surface that is fulfilled. Okay, it is a scheme of what is happening, and so you can do this kind of simulations and study different textures. Of course, these textures down on the lower surface, you are putting a smooth surface sinusoidal texture. That was to exemplify what you can do. Now let me go back to the slides. Okay. So what we did was to try to extend this algorithm. What you do here at the left is what you, after discretizing by finite volumes, you obtain something like this. You can write down an algorithm. This is a Gauss-Seidel-like algorithm. You recover the original Elrod-Adams algorithm when t is equivalent is 0, is identical is 0. And what we did was to try to extend this for some general t. The right side, you can see this operator. What it does is to mark down. First, you mark down the areas where the pressure should be, the cavitated areas where the cavitation pressure is not null, is something else, something positive. You mark them down and you try to impose the correct pressure there. We did some numerical exploration on this. We obtained some results. At least, you write this algorithm and you run it on the computer and you pray for it to converge. In fact, we compiled these results and published it in Technology International. And one of the results we've shown is that, in fact, this generalization of the Elrod-Adams could be used in order to simulate the blow-by. That is, when the gas pressure at the right side of the domain, it goes high enough, as intuitively can be thinked. If the pressure at the right side is high enough, the fluid downside of the ring, will be pushed to the left, and that is blow-by, and you want to prevent that. So this kind of extension can be used to predict these situations. Now that it was for one model. Let me know first how much time.
Alfredo, sorry to interrupt.
Yes.
So should we do the discussion after your presentation, or just in the middle of your talk?
I don't know. Gustina?
Would you prefer the discussion during your presentation?
I don't know. I was going to ask about the time. I think I have gone for 30 minutes right now.
But I think it's okay if Alfredo available to answer the question during your presentation. Yanti, hey.
Yeah, can you hear me?
Yeah, we can.
I have trouble with the connections. So the participants, you can ask the question during the presentations. It doesn't have to.
Alfredo, do you mind with that, or you
No,
prefer?
not at all, not at all.
Okay, so I'm just gonna make sure that the previous slide. So you are using grid-based solution. Unit volume, you said, if I'm not mistaken.
Yes.
Okay. So have you tried like physics informed machine learning to solve this?
No.
But you are aware of it?
No, we haven't used machine learning here. No.
Okay.
Not
So
at all.
all right. Okay.
I'm
okay.
aware. I'm aware, but like reading, headlines of some journals on partial differential equations. I know that they are using it for elliptic equations, and I'm not wrong. But no, we haven't. It could be something interesting to maybe in this problem, if you have some way to predict the cavitated regions, then you solve the problem, because if you know where the cavitation regions are, then you have an elliptic equation, right?
Yep.
I don't know.
Okay.
Maybe you could use machine learning to predict the cavitated areas, depending on the history of the simulation.
Oh, okay. So, but you have some data on the boundary and initial values of the.
Yes. You have the initial
models, right?
values,
Okay.
the boundary, the pressure, and the boundaries, and the initial values. That is the initial fields, right? The initial, the initial free fraction. So you know where the fluid is complete initially. You don't know pressure, but you know theta.
Yeah, and one more thing. So you also measure like during the experiment. Are you doing also experiments on this problem?
No, we have
no, just the modeling. Okay.
We have experimental results, but not from our group.
Oh, sorry to interrupt. Please continue.
That's okay. Okay, so that was for one model. Let's go for another model. Still in the Reynolds equation context, so still in the lubrication area. During these doctoral studies, we went for another possibility. That is a cavitation model that mixtures the Reynolds equation with the Rayleigh-Plesset equation. Okay. So first, what is the Rayleigh-Plesset equation? At the left side, this scheme accounts for a symmetrical bubble of gas. Okay, it is a sphere in 3D. And doing some assumptions, like this is placed on an infinite media. The far field pressure, and some other hypotheses, and the fluid is Newtonian, and you have some law to describe the pressure inside the bubble. For instance, an ideal gas law. You can, that is not necessary, I'm sorry, you just write down PB, the pressure inside the bubble. You can integrate the Navier-Stokes this time by where you use spherical coordinates, and you get to this equation, which is the Rayleigh-Plesset equation. Okay, so knowing the pressure far away from the bubble in time, you can recover the evolution of the bubble radius in the evolution of the bubble radius. Okay, here you have the some inertial terms. In the equilibrium, you recover the Young-Laplace equation and some viscous terms. So, but what we did is, okay, let's guess that we have a distribution of bubbles on the fluid. So locally, we will write R instead of a single bubble. We will write R as being a field that depends on X and T. So if we know the local pressure, that is written right down. If we know P, we have R. We have the evolution of the local bubbles. And you can couple both equations, because knowing R, you could recover, knowing the local radiuses of the bubbles, you can recover the fluid fraction, the gas fraction. And you can write the density, you can model the density of the fluid in terms of this fluid fraction alpha. Okay, so alpha is playing a role similar to theta in the previous model. So you can write down these both equations coupled. What we have done here was to replace the temporal derivatives in the electric set equation, formally replace them by the material derivatives for R. Okay, so you get these two equations coupled. And this we call this the Reynolds set equation. Yes.
Sorry, Alfredo. What are described for? Sorry, I'm not here before. What are?
I'm sorry.
What are described?
Okay, this time it is a field. The R will be what is the, if you assume a distribution of bubbles, what is the local radiuses of the bubbles? Okay. So if you have that R at x equals 0 at time t is 1 micron, that means that locally the bubbles in average have 1 micron. Okay, but this depends on the position and this field R. Okay, okay. So you have this coupling, and we played a bit with it. And as I said in the beginning of the presentation, you can do theoretical questions when you go with this kind of studies. You can do numerical studies. On the PhD, during the doctoral studies, we went on both lines. For the mathematicians, you can do questions of existence, uniqueness, stability of these solutions. First, numerically.
Before continue, Alfredo, sorry.
Yes.
Can I ask a question? Why are you interested in uniqueness of this model, of this problem?
Yes. First, because it wasn't studied. So
okay.
Nobody did it before, and second, because there is, in fact, a numerical interest in this. Someone has proposed these models, but I talk about this symbiosis that you have between the numerical part and the experimental part. Here you have this symbiosis between the properties of the mathematical problem and the numerical part. So if you have some mathematical support on, yes, what you are doing numerical work, and it seems like your numerical discretization converges towards something numerically, but you have the support, the theoretical support, that in fact there exists a solution. Okay, it is not only a numerical thing. I don't know if that answers. That gives you some support, some trust on what you are doing numerically. But of course, there is this interest of just studying the problem. If the problem is interesting or not. And it is interesting for the students, the students that are pursuing mathematics and are studying functional analysis. The theoretical questions we did on this problem. If you do a regular course or a regular discipline of functional analysis, you will be able to answer all these questions. The questions that we did on the theoretical work.
Oh, okay. So not numerical.
We also did numerical.
For the uniqueness, I mean.
No, for the uniqueness, no.
So I mean, I wonder whether we can do something like deflation, like deflate the equation to get another solution of the differential equation. Do you think that would be possible?
No, I don't know. I just don't
Okay.
know. We have existence and uniqueness on a simpler problem that I will describe now. On
Yeah,
the general
sorry.
problem, we don't have results on the well-postness.
Okay, sorry
don't
for that
know.
because currently I'm trying to work on that, like on the uniqueness numerically by using something like deflation.
Yes.
Okay, thank you so much. Sorry for disturbing.
No, well, you're welcome. Sorry. So on the numerical part first, let me just control my tongue. I will exit my tongue. On the numerical part, first you taking out the disregarding the initial terms, you get this simplified problem. First, you have the Reynolds equation, and on the second line, you have the simplified Rayleigh-Preset field equation. Okay, recalling that R this time is a field that depends on X and T, and so you get this problem here. And on the numerical part, that was the first subject we were interested. And there existed at that time, 2018, there existed some numerical works, but we implemented them. They just didn't work. Okay, you got unstable numerical solutions once and again, independently of the efforts. And what you can easily discover for the undergraduate students, you can the derivative that is in red, the marked in red, you can approximate it. You can approximate this derivative with forward Euler, for instance, as performed there, as written there, and that was what was available in the literature. Okay, and when you do like that, you can prove with a piece of paper and and a pencil, you can prove that this is unstable, numerically unstable. Okay, you discretize, and then you linearize your discretization. You discretize in space, you will get a series of a linear equation. Okay, and then a linear equation, and then you linearize it, and you can study its stability, and you will see that this kind of discretization implies an unstable numerical scheme. Instead, if you use the chain rule, so you do like this, and then this dr dt, you replace this, you substitute this dr dt using the second equation, you get something like this. Okay, all what we did was to use the chain rule and to replace the dr dt. Now, if you discretize the resulting equation here, you can see that now you have only dh dt, right? You don't have dr dt. So this time, if you discretize this resulting equation, okay, with some, I will skip the details. If you discretize this resulting equation, this time you repeat this. When you repeat this procedure of studying the stability of the resulting discretized evolution problem, discretized in space evolution problem, you will obtain. I will skip this. You will obtain that this time the problem is stable. And we pilot this and publish it also in Tribology International. For the ones interested, if you go through the paper, you will see that it's nothing too fancy. It's just if you know the Lévesque, if you study the Lévesque book, on partial differential equations, the numerics on partial differential equations. You go for the zero stability definition. You will see that all we did was to apply this zero stability definition to study the eigenvalues of the discretized problem, and that was all. Okay, that was for the first kind of models related to lubricated devices. I think I have maybe time for the theoretical part. I have used 49 minutes, haven't I? Can I continue, or you prefer to?
Actually, you can continue as you want.
Okay. Okay. Thank you. I will try to go faster. So I said that we first were interested in the numerical part of this problem. Okay. Let's go for the theoretical part. So this was, I got very lucky because on the first year of my PhD, I did this course on functional analysis. So I had some basic knowledge on PDEs, very basic knowledge on how to solve or how to study partial differential equations. And so I went to Lyon. There is a group actually interested in this problem, on theoretical questions on this problem. Okay, what we did at that time. Again, here you have the Rayleigh-Placet, the Reynolds-Rayleigh-Placet coupling. So the first equation is the Rayleigh-Placet with all these terms, and the second equation is the Reynolds equation. Just abstracting it a bit, you replace with auxiliary functions like f1, f2 till f5. Okay, so you abstract the problem. And you write down your hypothesis. F1 is smooth, whether it has a sang or not, etc. Okay, what about the well-posedness? Now talking to the mathematicians, what is the well-posedness of this evolution problem? And then, okay, first the Rayleigh-Placet equation, as written here, it is an evolution problem, but the thing is that you have this P that doesn't depend in principle, well, as written there, you have your unknown is R, but you have this thing here, this apparatus that is P. What do you do? So, but P comes from the Reynolds equation, right? So P, in fact, is this elliptic problem. This elliptic problem depends on R and its derivative, right? On the second equation, you have a dependence on R on the RDT. And so if you are lucky enough, this dependence will be smooth. And you, in fact, you can prove with the help of some functional analysis results and some Sobolev embedding regularity results, of Sobolev space regulated results, you can prove that in fact this P can be written as a smooth, with a smooth dependence on R and the RDT. Okay, so you can replace P on the Rayleigh-Placet equation. You replace it just by A of R the RDT with sufficiently smooth, so you can use the Cauchy-Lipschitz theorem. So you have automatically existence and uniqueness locally in time. Okay. Okay, that was for the existence. And let me go back. Yes, that was for the existence. Here, I previously I said that you simplify the problem, but you can see that at the left you have the full all the terms. So for somebody, Taufik, I don't know. I'm sorry if I mispronounced it. You have the full equation here, and that is how we went for these questions on existence and uniqueness, local in time. And what about stability? So this was for local existence. What about stability? The first step to study stability was to go to find for trivial solutions. Recall that I said if the gap between the surfaces is constant, if you don't have any region convergent or divergent geometrically regions, then the pressure is trivial, it's zero. Okay, so in fact that can be seen in the second equation. Here we separate, we write the gap between the surfaces as a constant h0, constant in space, plus some variation, h plus. Okay. So if h plus is zero, the solution is trivial. It's just pressure equal to zero and radius equal to the condition, the boundary condition. Or if the velocity, the relative velocity between the surfaces, you can think on the journal. If the journal is stationary, there is no, the fluid there will not be hydrodynamical pressure. Okay, so if U equals 0, the solution is also trivial. P equals 0, R equal to the boundary condition. So this is a trivial solution. And the first step was to extend this trivial solution by continuity arguments. Okay, and here we used the implicit function theorem. So you can extend on a neighborhood of this trivial solution. The trivial solution P equals 0, R equals something. This trivial solution you can extend on a neighborhood. So you can get non-trivial solutions. Okay, where H plus can be non-null and U can be non-null. There you have existence of, and for the stationary problem, right? The stationary problem that you get when you, I'm sorry, I went too fast here maybe. The second equation on the stationary problem, you have the second equation is the Reynolds equation, and the first equation is all what remain from the Rayleigh-Tesset equation when you write the stationary problem. Okay, the pressure is equal to F of R. So okay, so you got non-trivial stationary solutions, and you can prove. I skipped. In fact, you can prove by also basic functional analysis arguments and some results on stability. You can prove doing a spectral analysis. You can prove that you have stability. This neighborhood where you extended your solution, this trivial solution, there is another neighborhood inside of it where the solutions are stable. Okay. This was compiled and published also in 2019. So you can see that it took some time from, I went back from France in March 2018, and it took some time to be published, this work. I would also recommend for the undergraduate or graduate studies students in mathematics, maybe they will, if you want a trivial example of using these functional analysis tools, you can go for this paper. It's nothing too fancy. Maybe you will have some entertainment. Okay. So now I end the part of relative to lubrication. I wanted to comment that, well, when you start a PhD, maybe maybe not. You can have this idea of being married to an area. I will do this research and I will do it for the rest of my life, maybe. Or maybe that was the idea I had when I began the PhD. But the thing is that after I discovered that now you can, this is only the start of your scientific career. Okay, so after the PhD, you can go to other areas, study other problems, completely different. And that was what occurred to me. And during a postdoc here in the institute, I went to another completely different area, still in fluid mechanics, but totally different. This was fluid flow through porous media. And I want to briefly present this in order to have time for the second presentation. What is it? So, and what is its industrial application? Here we have an example of a numerical result, four numerical results, of a representation of the intensity of a flow field through a porous media. Okay, so down below you can see the red. The more red, the more intense is the flow. And from where it comes. In one of the applications of this kind of modeling is in the petroleum industry. Okay, so one of the techniques to extract petroleum is you perforate the earth. You do some wells. Okay. In this scheme, you have a well on each corner, and on the center you have another well where you will put a negative pressure. That is, you will, instead of injecting, you will suck fluid. Okay, so in each corner you are injecting water, for instance, and on the center you're sucking the whatever it comes from there. Okay, so if there is petroleum, eventually the water will push the petroleum towards the center, and it will exit the domain, the terrain through this center well called production well. So that is where it comes the interest of this kind of studies. But the thing is that you can imagine that the scale necessary to have accurate results is of around each cell, computational cell. If you think of finite volumes, each cell has to have in the order of 1 meter, but you have fields of kilometers of three-dimensional fields of kilometers of size. So you have a huge amount of degrees of freedom. Okay, so it is too expensive computationally. So an alternative for this, instead of solving for all the degrees of freedom, you can use multi-scale methods. What is it? First, let me show you the model, the mathematical model. We're talking of one of the models when talking of porous media to recover the velocity field. Okay, U at the right side of the screen. U comes from the Darcy's law. So U is equal to a parameter. First, the parameter K there, that is a tensor describing the permeability or the local permeability of the media, okay? And the gradient or the pressure gradient, okay? This is the Darcy's law. Lambda is the mobility. We are talking of two-phase flow, but I will not speak too much about this. But basically, you are modeling a two-phase flow. You have the mixture of water and oil. Okay. And so knowing U, knowing the field velocity U, you can put this in your transport equation and solve for one of the phases. And you make the assumption of the media to be saturated, totally saturated. So you only want solving for the water fraction, you will have the oil fraction. Okay. So you put this in the transport equation for the water saturation. That is your model. But as I said, the size of the problem here, the size of what you want to model is the problem. It's too big. Okay, too many equations. So what you do, I will go fast here. What you do is to decompose arbitrarily. Principle decompose arbitrarily your domain omega in many subdomains, smaller subdomains. Okay, where if you write down your problem there, you can solve it fast. Okay, because it's very small compared to the total size. It's very small. What you do here is to write down these previous equations weakly. So you write integral of, and to couple up these problems to record the global problem through the skeleton of this decomposition. And you weaken the problem. You write a space of functions on the skeleton, okay, but you go for a space of lower dimension on the skeleton. So what you do is to condensate degrees of freedom on the skeleton. When you discretize, you can translate this weakening into condensating degrees of freedom, and you impose a weak continuity of U, the field U, and pressure. So what does it imply computationally? You have to solve many problems. You have to construct a basis of solutions on each of these domains. You have to solve many problems. You construct a basis, okay, here, but you can do it fast, much faster than solving the whole problem. And then you solve a small problem, a small linear problem to solve for the coupling, for the weak continuity of pressure and the velocity field on the skeleton. And what you will obtain is pressure and the velocity field on the skeleton. Okay, and then with P, with the pressure field, and you on the skeleton, knowing the values of P and U, the approximate values of P and U on the skeleton, you can put this again on the subdomains as boundary conditions and recover a global solution. Okay, and on the work on the postdoc, we focused on the computational part of it. So how to distribute these many small linear problems on a cluster, on a supercomputer, how to do this. And well, in principle, the decomposition is arbitrary. So how the computing time depends on this decomposition, on the skeleton. If you put more degrees of freedom on the skeleton, I will skip this. And this was compiled also and published in the last year, 2000. Well, it was accepted early this year. And so you can see during my career, but I'm just starting my career 3 years ago, since I finished my PhD. But I went through many different areas. That is one of the messages I want to leave for the undergraduate students. I went into numericals. I studied a bit of theoretical questions on partial differential equations. I went also into computation, computational questions. Here for this word, or focus was on coding fast. I mean, on doing a code that runs fast on a supercomputer. So you can you don't need to be fixed on an area. You can explore pursuing the scientific career and applied or in pure mathematics. That is the end of this presentation. Thank you very much. Agustina?
Yep, thank you for the presentations. So we have questions. Can you hear me?
I'm listening. Listening.
Okay, the first question is it possible to use calculus approach here?
Calculus approach?
Yeah, maybe I think it's elementary. I think.
In what model?
Or maybe I can find more. Yeah. Maybe the question is, can we solve the problem analytically, or
analytic? It depends. On all these. Yes. On almost all of these models, you have some analytic solutions, in fact, and they help you to have some intuition on what the solution should be or must be. Okay. For instance, in the video I've shown of the, let me go back here. I showed you a video of this ring, right? And this was a numerical solution. It doesn't have that particular case. Up to my knowledge, there is no analytical solution for that particular case. But if the texture is, I'm sorry, is instead of being sinusoidal, is made of squares, okay, and if the solution is, if the lower solution is just squares and the upper surface is flat, you can write down analytic solutions, and you can learn from these analytical solutions. That is for this case. You can learn some properties of the solutions and to have some intuition on how this should behave. Okay, and even for this case, for well, the right present equation has analytical solutions. When no. For the Larry present equation, the bubble, you can assume that the pressure oscillates in time, and so the bubble response, the dynamic of the bubble is very interesting on how it responds to this oscillation, this excitation coming from the pressure field. And there are books written on this. The solution of the Rayleigh present equation. You can look for it, and you can learn. You have different dynamics depending on the frequency, and you can predict. The solution of the harmonic oscillator. You can predict that this, how do you say that? The frequency of oscillation of the bubble, you can predict it theoretically in function of the frequency of the pressure field. And what else? For the last model, for this model, there are also, up to my knowledge, for this model, for this exact model, two-phase flow, there are no analytic solutions. For other similar equations, for the Bapak, there is a toy problem, I'm sorry, I will not recall right now, but when you study this kind of problems, the Burger's equation, right? The Burger's equation. This is related. This two-phase flow problem is related to the Riemann problem, and the Burger's equation is an interesting equation that has analytic solutions for some cases. And again, you can recover some interesting properties from studying these analytic solutions. So there is this feedback coming from the analytic solutions for the numeric. Any other questions?
I hope this will answer it, the question from Mr. Rani. And the second question is, what is the advantage or reason of this your research in math in the future?
I'm sorry, I didn't get it.
What is the advantage of the research in math in the future?
Math, not to industry. Maybe the question is the advantage math to math, right? Not math to industry. This is the question. Can you catch the question?
Let me augment the volume here. Okay, again, please.
I'm sorry. So the question is, what is the benefit of this research for math?
For math, what does it mean for math? For
like in other
the mathematicians.
I think the one who asked can like unmute and ask himself.
Oh, yeah.
Pak Roni, wasn't it?
Yep. Pak Roni, please.
You can ask question from
okay.
Malang.
Yes. I'm so sorry. I mean, the second question is, what are the advantages of this research for math in the future? I mean, the math is the global, the global scope. I mean, for the next research, not for mathematician only, but also for the maths itself.
Whoa.
Thank you.
Whoa. Okay. Whoa. That is a big question. Oh. Okay. I would try to say an answer. You know, these problems, all these problems have a huge industrial, not only academic, but a huge industrial interest. So that is where mainly that is mainly from where the money comes, right? And that is what makes possible in many contexts. That is what makes possible to do research, even pure research. So you know, this catalyzer. How do you say that? For these problems, having an industrial interest. How do you say that? I think I will repeat myself. It stimulates, okay, the funding of pure research. So for math, I think I have just answered. Having this connection between industry along with this numerical community, if you want, is helping math to continue. You need somebody to pay you for your work. I have seen examples of pure mathematicians that have this contact. They help with the industry, and they continue to do fundamental research. I don't know. I maybe I have answered the question. I don't know. It's a big question.
Correct me if I'm wrong. You're more to the scalability of the numerical solution of this problem, right?
I'm sorry?
You are more into the scalability of the numerical solution of the mathematical model, right? Yeah, the empirical solution, if I'm not mistaken. Is that correct?
For one model, for this model?
No, I mean like the last paper that you mentioned. Yeah, the HPC simulations.
Yes.
You're concerned about the scalability of the numerical solutions, right?
Exactly. Yes. We are concerned about it.
Yeah. So for pure mathematicians, when they are dealing with problems that does not have an exact solution, this numerical solution can help them like to get an idea or to check whether their solution is correct or not. I think that is also very useful for those who are interested in the exact solution. But rarely people will solve it.
You will solve. Yeah, exactly. You will rarely have a exact solution. What mathematicians know this better than me. I shouldn't. You will have properties, and you will know how your solution responds to changes on some parameter. If maybe your solution is monotonic with this parameter, maybe your critical points. How do your critical points answer to changes on the parameters? You will know if your solution is, I don't know, positive in some circumstances. Like general properties of your solutions rather than the exact solution.
So you're working on a forward problem, right? Trying to approximate the solution. Do you also work on the inverse problem of your equations?
No, I haven't. This kind of simulations are related to inverse problems. This kind of yes, there is. I wouldn't. I cannot say too much about it, but all I know is that you can predict one of the applications of this kind of simulations are to predict the field. You have, here your data. You are assuming here that you know the permeability. One of the you can use this kind of simulations for instead predicting K along an inverse problem. Yes, but I haven't done it. I know that it is possible, or at least it is an hypothesis that is being studied.
Yes. A possibility for collaboration. Thank you so much for awesome presentation.
So the next question is from the lecturer of analysis, Ibu Mariani. You can ask Alfredo directly, Miss.
Yes, thank you. Thank you very much for the I want to ask one question for Mr. Alfredo. For your problem, is there any open problem for us, maybe which study in analysis approach for your problem? Maybe this is only my question. Thank you very much.
You're welcome. Thank you for the question. Yes, in fact, this problem here is being studied. This group in France is still studying this problem, and when you here, let me see if I will complete problem somewhere. I didn't. There is yes, here relative to the numerics, but here. This term here was neglected on the theoretical works. You don't see this term here, but the bubbles are being convected, or it is reasonable to assume that the bubbles, these bubbles are being convected by the field, by U. Okay, but here on the first equation you don't see a convection. You don't see U dr U nabla R. Okay, you're not convecting R. Okay, but there are some numerical works on this. So this term is being neglected in that paper. There are open questions. What happens with the web postness of the problem when you add up this term? It is an open problem, up to my knowledge.
Okay. Yes, okay. Thank you very much.
You're welcome.
Thank you very much. Anyone to ask the question, you can raise your hand and ask directly.
Maybe I want to add the theorem slide after this. I think after this slide, the theorem.
I'm sorry, I didn't.
I want to ask about the theorem slide. Just one.
In which slide do you?
23. 23. Yeah.
Yeah.
The theorem. Now this one. 21. Oh, sorry. 21. You
21,
highlight.
yeah.
You highlight here the solution
Yes.
of PS depends continuously on H plus. Is it possible that the solution independent of H? Why you highlight? It's eye-catching. Sorry.
The continuity. Is it possible again to have the contrary? Okay, the opposite. Okay, this highlighting.
It's the height of the nucleus, right?
Yes,
Sorry.
yes, yes, yes. Yes. For when it comes the continuity, let me recall why. This continuity, if I'm not wrong, this continuity was used for, well, let me yes, you use this continuity, I say continuity without the specifying. So you have some kind of regularity of the solution with H and with U, and you use this continuity for the stability results. Okay, if I'm not wrong, you need this continuity when you do the stability analysis. Okay, you need this continuity, this regularity of the solution with this parameter H and U. If I'm not wrong, I should go for the details on the paper. But you need this continuity, yes.
Thank you.
But it's in red. Okay, you asked me if the opposite is possible. It is in red because you will use it for stability, no, only because of that.
Okay, thank you.
You're welcome.
There more any questions? Or can we continue for the second session we in?
I think so. Can continue.
I have a question.
Or do we?
Rian,
Yes,
there is
please.
someone- Mr. Zakaria.
Okay, yeah, thank you. Dear Alfredo, Jaramillo.
I'm sorry.
Okay. I have a question, general question for numerical methods. As far as we know, many numerical methods can be used in solving mathematical model problem for industry, especially those involving partial differential equation. So my question is, which type of numerical methods do you prefer to use to solve mathematical model problem in your current research?
Oh, okay. Okay. Right now, on my current research, right now, I didn't show what I am doing right now, but on okay, it has two. I think I can answer in two ways. During on the first part of this presentation, I talked about the hyperbolic nature of the problem. You had this here. You had these cavitated areas where the problem is hyperbolic. So we used finite volumes because you needed mass conservation. Okay. You can show on this context, you can show that for accurate results, okay, mass conservation is a must. Okay, you can show that this model is mass conserving, and so you need a numerical method that respects that. Okay, and finite volumes is a kind of numerical method, finite volume method, deliver that kind of solution, a numerical solution, okay, a discrete solution or a discrete method that is mass conserving. So during these studies there, I used finite volumes method. That is the first part of the answer. Right now I'm working with heat transfer, mass and heat transfer on boiling problems. So basically, it is a fluid that is in touch with a heat surface, and because of this heat, it will boil. And so we are using lattice-Boltzmann methods, the lattice-Boltzmann method, with some particularities. That is because classical methods, they don't recover this nature of the I can maybe show you a video on it. No, it will take it will take too much time maybe. Let me see if I just a second. No, I'm sorry. Well, anyway, so when the fluid boils, you take these kind of simulations. One of the fields that you predict is the density, and the density on the vapor part of the fluid is really small. So there is an interface between vapor and fluid. This interface in classical methods like fluid fraction volumes, if I'm not wrong, if I'm not mistaken the name, this interface is, you have to initialize your simulation assuming you already know where the vapor is. Okay, so you have to put some bubble around the place where the heat is being applied. If you assume that all the domain is only liquid initially, there is no vapor, the classical methods are not able to predict boiling. Instead, Lattice-Boltzmann is able to predict this boiling. Okay, so there will naturally, in Lattice-Boltzmann, there will naturally appear an interface of vapor and fluid. A bubble will grow, boiling will take place. So we are using Lattice-Boltzmann right now, and it's not me who is. I didn't select this method. It is the method, the state of the art for these kind of simulations, because we are interested in boiling problems. I don't know if I answered well the question.
All right. Thanks so much, Alfredo, for your.
You're welcome.
Thank you, Pak Jack, for the questions. I think now we can go to the second sessions, but before that, maybe Alfredo needs a break. Let's have break for 5 minutes.
Okay.
Okay. Yeah, we will have break
Thank you.
for 5 minutes.
Kita sambil isi daftar hadir ya, teman-teman.
Alfredo. Okay, welcome back again. We will start the second sessions. In this second session, Alfredo will share some over from his university. First is a video of the university.
Kelihatan nggak share screen aku ya?
Belum. Tadi sih loading, tapi sekarang hilang.
Belum.
Udah.
Suaranya nggak kedengeran.
Alfredo, you can share some slide.
Yes. Okay. Is my audio working? Please, some confirmation. Is my audio working? Are you listening to me?
Yes.
Yes. Okay. Thank you. So I will share. This second presentation goes on describing some of the opportunities, or if you are interested in pursuing a career in applied mathematics, pure mathematics, computer sciences, the Institute of Mathematical Sciences and Computer Sciences here in the University of São Paulo could be a good opportunity or a good choice. So I will talk about a bit about it. This is where I did my master. This place is where I did my master and my PhD and a postdoc too. It is a highly recognized institution in Brazil. So first, where is it placed? This is where I'm still living, San Carlos, the city of San Carlos, are approximately 200 kilometers or 4 hours by bus from São Paulo, the capital of the state of São Paulo. So if you are interested in coming here, you will arrive first to some international airport at São Paulo maybe, or Campinas, and from São Paulo it will be 4 hours by bus. You have also Rio de Janeiro here, better known maybe, placed at 6 hours by bus from San Carlos. If you are interested in coming here, I will first describe what about the city. What about San Carlos? So thinking on how to describe the city, I should say that it is a very nice city to live in. It's a medium-sized city, around 200,000 inhabitants. The weather is, starting with the weather is nice. In winter you have is not too cool. Winter is dry, so you don't have the combination of cold plus rain. And summer is a bit rainy, but warm, not too hot. 33 degrees maybe maximum. So it is very nice. The weather is very nice. It's comfortable. São Carlos is known as the capital of science and technology of Brazil. Two important universities are placed here: University of São Paulo and the Federal University of São Carlos. Both are internationally recognized universities. Well, the capital of science and technology also because there is important industry taking place here, like Volkswagen or Faber-Castell. Okay. I mentioned earlier about the funding, from where the money comes. In the case of Brazil, you have three main entities when speaking of public entities. You have here CNPq, the one in the middle, that is the coordination for the improvement of higher education personnel. It depends on the Ministry of Sciences, CNPq. On the left, you have CAPES, which is the coordination for improvement of higher education personnel. CAPES depends on the Ministry of Education of Brazil. And at the right side, you have here in São Paulo, in the state of São Paulo, you have FAPESP, the São Paulo Research Foundation, that depends solely on the state of São Paulo, okay, on the the government of the state of Sao Paulo. So you have money coming from the federal government, from the state government, and I should mention also, in fact, the first postdoc I did was financed by Petrobras, the petroleum oil company, Brazilian petroleum oil company. And the money comes, they put the money through some institution, public institution. So you have finance funding coming from industry. That is important. You have this collaboration with industry and public entities, educational entities. The institute has undergraduate and postgraduate courses, as I said before. It also has opportunities for postdocs and visiting professor opportunities. Here I want to say that one first step, if you are an undergraduate student or a postgraduate student, maybe you did your master and you're interested in pursuing a doctoral degree in other place, like here in Brazil, the first step would be to directly contact somebody which you are interested in working with. So there is this professor that has developed research in this area, you are interested, so write directly to him, because he, not only because of knowing him, there is some funding, there is some money that is part of a research group. I mean, this money goes to a particular research group, and that research group administrates this money, these scholarships. So you can obtain these scholarships directly from the institutions, these institutions, or you can go to a research group that already has these scholarships. So you can directly contact this professor, whoever you want to work with, and to ask him. And that is a good first step if you are interested in working. As a reference on the values of the scholarships, if that interests you, for a master, it is around, you will obtain something around 1.2 minimum wage. That is for somebody that lives alone. That is okay. That you will be okay with it, and mainly because there is, in the University of Sao Paulo, you will also have cheap meals. Okay, the meals, the dinner and the how do you say lunch is really cheap in the university restaurant. So you will not spend too much money on feeding yourself. For that, it was for master. For doctoral, it goes higher. For doctoral studies, it goes something like 2.4 times, doubles for 2.4 times the minimum wage. So that is much better. And for postdocs, it varies. It oscillates between 4 and 8 times the minimum wage. So, well, if you are pursuing a career that would be interesting. I want to say too that what happens with language. Brazil, people here in Brazil talks Portuguese. That is the native language in Brazil. That shouldn't be a big problem, depending on the demand. The discipline, the courses could be performed offered in English. Myself, when I came here, I didn't have too much problem, but I have the advantage of speaking Spanish, so it wasn't too difficult. But I had these disciplines, these courses provided in English, so that aids the process. All the professors will be, or well, all the professors I've known, they have a good English level, so that wouldn't be a big problem. Okay. This was for the video.
Fredo, can I ask you?
Yes, of course.
For master degree, we have some courses, right? Does it deliver in English or Portuguese?
Yes, depending on the demand, they will be provided in English. The rest will be in Portuguese. Yes.
Okay, you can continue.
Okay, and in the video you saw that there are many programs. One of the programs is the in the computer science and computational mathematics area. There are many research areas in the video where they were resumed, summarized. Particularly this was my area, the program on computer science and computational mathematics. You can see the last one was my area, computational fluid dynamics. Okay, so it is applied mathematics. That was the area where I worked, where I studied. But you can see there are many other research areas if you are interested in maybe computation, in artificial intelligence, visualization. My area was computational fluid dynamics, complex systems, the areas in pure mathematics. So there are many research areas. You're welcome to visit the institute website. In particular, in computational fluid dynamics, there are these areas. I worked in computational rheology, or lubrication, and modeling and numerical simulation in lubrication. There is this area. There are these areas also of moving surface flows, and I haven't worked in the other areas, but I worked mainly on lubrication and computational rheology. There are these other areas if you're interested. And now I want to share, to finish. Let me see what the time is. Yes, we have some time. I want to share the experience of two of my colleagues. So one is Dr. Steven Paz Sanchez. He's from Colombia. He obtained a degree in mathematics. So you can see he started doing pure mathematics, studying pure mathematics. He obtained his degree in mathematics in Colombia. Then he went to IMPA. IMPA shouldn't be unknown for you, for the mathematicians. The Institute of Applied and Pure Mathematics in Rio de Janeiro. He did his master there at IMPA, and then he went to the ICMC here to pursue his PhD in applied mathematics. He was my colleague during that period. Then we did this together, this postdoctoral study at the ICMC also, and fluid flow and porous media. And now, from last year, he's an associate professor in the Universidad del Valle in Colombia. So you can see he started in pure mathematics, he went to applied mathematics, and now he's a professor. I can say that I don't know anyone who haven't had a good career after pursuing this post-graduation in the ICMC. They're whether working on the industry, or doing research, or they are pursuing an academic career. Myself, I'm going to United States in July to work on an institute depending on the Wyoming University. So your projection as a researcher is good. It's more than good. I will also show a video from Professor professor, from Dr. Guilherme Ferraz da Ruda. He's from Brazil this time. He got his degree. You can see he started in engineering. He started doing obtaining a degree in electrical engineering. After that, he did his master in computer science and applied mathematics and his PhD. We were colleagues also at the SCNC, but he went to pure mathematics. He works with complex networks, and right now he's a researcher in Torino, Italy. Gustina, can you please share the video of Stevens? My idea here is these are two examples of colleagues of their careers, and they will share. Stevens will describe briefly what is this area of computational fluid mechanics. Okay, and after that, if it works out, Dr. Guilherme will describe also briefly what kind of questions can be answered in complex networks, which is his research. Please, Gustina.
By in, please share the video that.
Thank you.
That I see before.
Tadi kayaknya Stephen dulu enggak ya? Urutannya benar itu ada.
Stephen dulu katanya.
Stephen dulu. Tadi urutannya jurnal dulu.
Jurnal kayaknya sama stok kali kayaknya.
Hah?
Tadi Stephen dulu.
Dulu ya.
The first is Stephen, right?
Yes, it can be Stevens. It can be Stevens or Guilherme. No problem on the order.
Oh, no problem on the order. Okay.
No, sorry. Let me see.
Itu bukan ya? This one?
Kayaknya putar aja deh semua videonya.
Ya udah tunggu aja. Ini tadi bukan?
Iya, ini udah di-share kayaknya pas tadi.
Okay, next.
Hi,
This one.
I'm Steven Thomas.
Yes,
I'm
that is
assistant professor in the
that is
Department of
Stevens.
Mathematics at University of Valle in Cali, Colombia. Together with Professor Gustavo Buscalia and Professor Roberto Ausas, both of them from the University of São Paulo in Brazil, we work in the field of computational fluid dynamics, CFD for short, specifically in computational microbiofluidics, in which we translate to the computer physical models that describes the interactions between microswimmers and the surrounding viscous fluid. This is a particular case of the fluid-solid interaction type of problems and its numerical simulation. Among many interesting questions regarding computational microbiofluidics, we try to respond to a basic one, which is how a small entity like bacteria or microrobots can attain net displacements, knowing that the viscous force of the ambient fluid rules their world. Microswimmers acquire their swimming capacity as a consequence of external or internal force, resulting from their interaction with the viscous fluid in which they are submerged. The configuration of the microscopic body is transformed into a set of unknowns for the corresponding fluid-solid interaction problem, also or the fluid-swimmer interaction problem, coupled to the equations that describe the dynamic of the surrounding fluid. Typically, microscopic biological creatures perturb their body or use their cilia or their flagella to prepare themselves. So models like the Squirmer model are considered in fluid-solid interaction problems to understand the behavior of near as well as far away velocity and pressure fields, coupled possibly with solid concentration fields. On the other hand, a basic artificial microswimmer, like the one consisting of 3 inline spheres with 2 compressible arms between the spheres, can attain net displacement when a sequence of non-reciprocal movements are performed. This microrobot can learn non-reciprocal sequence of movements, or states, so as to move towards a specific direction, by randomly exploring the movement's possibilities several times in several orders, and receiving rewards during that exploration. This is one example of reinforcement learning. Other cases, like the worm-like swimmer, which is a generalization of the previously mentioned swimmer, and the snake-like swimmer, are of important interest for us, because they involve more states or configuration. So, to learn to swim and to analyze the hydrodynamic interactions is more difficult in terms of numerical simulations.
Sorry. One more, right?
Yes, one more.
Hi, I'm Guilherme Ferraz de Arruda, and I'm a researcher at Sentai, a research institute in Turin. Together with Professor Francisco Aparecido Rodrigues from the University of São Paulo, we worked in the field of complex systems, and more specifically, on the analysis of spreading processes in structured populations. In that case, we are interested in understanding how a disease or a piece of information might travel in a population. Our goal is to have a mathematical model that is as close as possible to reality. To achieve this, we must take into account the heterogeneities inside our population. In our society, some people are more popular than others, having more connections than others. This will have an impact on both disease spreading and also in information or rumor spreading. Mathematically, we model our society as a graph, where we have nodes, which are the individuals in our population, connected by edges, that can be friendship relationships, for example. On top of that population, we associate a Bernoulli random variable to each node in our graph. In other words, what this variable is doing is telling us if an individual is infected or not, or in the case of the information, if a given person is aware of a piece of information that has been spread in the graph. The final ingredient in our model is how this set of variables evolve with time. This will be done by associated independent Poisson process to model the spread of the disease or information, as well as the healing or the loss of interest in a rumor. Disease spreading is quite a well-studied process. The most interesting question here is the existence or not of a critical point. In other words, is there a spreading rate in which below it the disease should go extinct and above it the disease should survive? If so, another interesting question would be, what are the dependencies of this point? Interestingly, we can show that this point can be determined by two main factors: the biological aspects of the pathogen and the pattern of connections in our population. It is actually quite surprising that this point might even go to zero if we have individuals with too many connections. Another interesting fact about this process is that for any finite population, the disease should always disappear. However, the time it takes to go extinct can be extremely large. To get a feeling about this fact, we might think about this process as a sequence of coin flips. In any case, a computational simulation is not so far from that abstraction. The probability of getting a sequence of 100 heads might look very low. However, if we keep flipping the coin indefinitely, it tends to 1. And to show this, you can look at the figure on the right, where all the different initial conditions might get to a stable state, a meta state, and then get to the observing state with no infected individual. But the time to get there is around 10 to the 6. Okay, finally, to show how rich this process can be, we show the results of a few simulations, where we just changed the initial seed of the spreading. We can clearly see that the same process can have a number of different outcomes. Here we show the example of Italy, where we started the process in Milan, Rome, and Palermo, and we can see that the final solutions for our model is quite different depending on where you start the process.
Okay. I cannot hear. I think there is problem with your
microphone.
Alfred. It's Bayin jelas nggak? Apa dia aku yang nggak jelas?
Nggak.
No, your voice not clear.
Let me see.
Oh, okay, it's okay now.
Is it well now? Is it?
Yeah, it dropped now.
Okay. So I just wanted to finish the presentation by sharing some links regarding the university and the opportunities you would have. Maybe I can, well, you can take, I don't know, a screenshot of these links. Just 1 second, let me share the screen again. There it is. So these links are the links I wanted to share. You can take a screenshot maybe to save them. At the last one, for the ones who could be interested in doing a postdoc, postdoctoral opportunities are being published there. There are all type of opportunities from all the science areas that are being worked in Brazil, in São Paulo. FAPESP, recall that FAPESP is an institution here in funding institution here in São Paulo, the state of São Paulo. So you can have from biology, chemistry, social areas, okay. And the first 3 links are related to the ICNC, okay. Some information on admission, international collaboration, and the research catalog, the areas that are being studied with some description of each area. So this could be of interest for you. And with that, I end this second presentation.
Okay. Paroni, I think this link is answer your question, right? Do you need more explanation? Paroni?
Enggak.
Okay. So, okay, thank you, Paroni. So, Paroni asked about scholarship. I think this link is, we can find more information about scholarship through this link, right?
Yes, but as I said before, for scholarships, the first step I recommend as a first step, first to look for what do you want to do, what area do you want to study, with which professor, or at least what research group, and then to write directly to this research group. Okay, that is the best. I think that is the best way regarding a scholarship.
What you did?
That is what I did.
Ah.
Yes, that is what I did.
So the scholarship in your case, the scholarship came from the research group or the government?
In my case, it came from the government, but I have received from the government, from the research group. Well, from the government and from their research group. The first postdoc, the scholarship of the first postdoc was from the research group.
But the first approach is to contact the professor you would like to work with first,
Yeah,
right?
that's my opinion. Yes.
Yeah. Thank you. Is there any question from other participants, please? Or from our lecturers? Cukup?
Already midnight in Brazil.
Okay. Okay, thank you very much, Alfredo, for the wonderful talk and discussions. We hope that we hope that our students will be more motivated to study math, as it has application in industrial by establish some models in fluid mechanics, and also, it also gives some idea for a lecturer and researcher in Indonesia to have a research collaboration, maybe with you in the future, or other researchers in Brazil. And I will close this seminar and thank you for the all participants and the guests for taking time of your maybe your holiday, since today is holiday or you are still working in the holiday, to join us today. And thank you very much for all of you.
Glad for having had this opportunity.
Yep.
Thank you. Thank you very much.
Thank you. And see you in the other seminar.
Yeah, other opportunity. Thank you very much,
Good day for
Alfredo.
you.